I welcome you all in this lecture on frequency response, and this is a sub module for the course which you are going through, that is modeling and simulation of dynamic systems. In previous lectures we have been seeing we have seen the dynamic model, the ways of deriving the dynamic model of systems, and one of the method has been using the what we say that we find out the equations, equilibrium equations, okay, wrote the got the expressions in terms of the differential equations. And now once you have these models, then the thing is that we are interested in finding out the response when it is subjected to certain input, okay, how that is the output is going to be. So previously we have seen when the system is subjected to say the step input, ramp input, it is always interesting to know what happens or how the response of the system appears when the system is subjected to a sinusoidal input. So, this is what we are going to see today under the heading what we call it as frequency response, and our aim of here is to see if my dynamic system is subjected to a certain sinusoidal input, what the output is coming, okay, or how the output what is the output of it, okay. So, as I said, sinusoidal input is an important input in design and analysis of systems. And say if we take first order system which is described by say this differential equation, a first order differential equation, say a1 dx by dt plus a0 x is equal to b0 y, where this y is input and x is output, okay. Now suppose this system is subjected to a certain sinusoidal input, let that sinusoidal input be of unit amplitude sinusoidal input which is given by say y is equal to sin omega t. Now when this system is subjected to this input, our interest is to see that what is happening to the x or how we can determine the x. So, I can substitute this y is equal to sin omega t here in this expression, and this is what we get b0 sin omega t, and of course my left hand side remains as it is. So, what I have is say a1 dx by dt plus a0 x is equal to b0 sin omega t, okay. So, this is what we are going to have. Now, the thing is here we know that the sinusoidal functions have the property that when differentiated the result is also sinusoidal with the same frequency, okay. So, if I differentiate the say sin omega t, then what I will get basically is omega cos omega t, okay. So, you can see that this differentiation also has got the same frequency as that of the input. Of course, this amplitude has been changed. So, thus output is expected to be of same frequency, but different amplitude and phase than input is there, okay. So, this is what is going to be, and we can come to this conclusion that whatever when this system is subjected to a certain sinusoidal input, the output is also going to be sinusoidal. We can conclude that because this right hand side is a sinusoidal, so naturally the left hand side also has to be sinusoidal, but of course as I said you are going to have the different magnitude and the different phase angle, okay, that we will be seeing further. So, these sinusoidal signals which I have been talking about, they are better represented by a phasor. Okay. So, phasor. So, say for a sinusoidal signal, if I talk about say V is equal to capital V sin omega t plus phi, here this capital V is the amplitude, omega is the angular frequency and phi is the phase angle. Now, this sinusoidal signal can be represented in a phasor by a line of length, say absolute value or magnitude of V making at angle phi with the phase reference axis. So, this is how we can do it. Okay. So, you can see that the representation of a sinusoidal signal by a phasor. So, suppose this is my sinusoidal signal, okay, and here you have the angle relative to axis OA, hence time. So, here you see that this begins with say phi here. So, there is a phase angle of phi and say this magnitude is represented over here, okay, and of course, that has got say value of V. All right. So, this sinusoidal signal can be represented by a phasor here, okay, and as I said, this phasor has got an magnitude V and at an phase angle phi. So, another interesting thing is that these phasor can be described by complex numbers, okay, and we know that the complex number is represented by x plus j y, where x is the real component of it and y is the imaginary component of it. So, here you can see that we have a real component say x and imaginary component y, then the complex number can be represented as x plus j y. Okay. So, on this graph you can see that the imaginary component is represented along the y axis and the real component is represented along the x axis. So, corresponding x comma y, actually these are the Cartesian point, and these Cartesian point x comma y actually represent this complex number, okay, and if this x comma y point I join with say origin of this coordinate system, then this represents the phasor. So, here the phasor in this one, you can see that the phase angle, that is we can find out if I just take the tan phi of it. So, this tan phi will be y by x and the length of the phasor will be basically under root x square plus y square. So, the length of the phasor is under root x square plus y square and the phase angle is given by tan phi is equal to y by x, okay. And again you see that this x is actually the horizontal component of this. So, I can write x as say amplitude of V into cos phi and y is the vertical component of it. So, I can write this y as magnitude of V into sin phi, okay, and then I can represent this vector this sinusoidal signal as a phasor V is equal to x plus j y or V cos phi plus j sin phi, okay. So, you can see that what basically we have done is that the sinusoidal signal we have converted it into a phasor, okay. Sinusoidal signal has been converted into a phasor with the say phase angle phi and the magnitude V. So, there are certain interesting thing which we can look at for the phasor. Say for example, here say we have a phasor of unit magnitude along the real axis. Okay. So, I can represent this phasor as 1 plus j 0, 0 because here the imaginary component is 0. Okay. Now, suppose I rotate this phasor by 90 degree like this. Okay. Then what will happen? This will be coming to this position. Okay. And this phasor will be given by what? Only j component. Okay. Because a real component is going to be 0 here. Now, you see that what essentially we are doing is that if I am going to multiply this 1 plus j 0 by j, okay, then I am going to this one. Okay. So, what does this actually mean is that the multiplication by j to this complex number is actually meaning that we are turning this phasor by 90 degree. Okay. Again, let us say that this phasor further turns by 90 degree, that is it aligns with the real axis along the say negative direction here. Okay. Now, this can be represented by -1. Okay. So, and of course, this operation we can achieve say it is only 90 degree rotation with respect to the previous one. So, if I multiply this by j, then what I will be getting is j square, and the j square is nothing but j square is nothing but -1. Okay. So, I get the -1, or I can what I can say that with respect to this one there has been 180 degree rotation. Okay. Or 180 degree rotation means that what I have done is that I have multiplied this by j square. Okay. So, if I do this, then this is what I am going to get -1. Okay. That is, for a 190 degree rotation you have to multiply with j, for 180 degree rotation you have to multiply by j square, and similarly for 270 degree rotation you have to multiply this by j cube. Okay. And you will be getting it the minus j, because when you multiply with j cube this is what you get, and this you can write as j into j square, and this is j square is -1. So, this is what you get as the minus j. Okay. So, this is 1 plus j 0 is 0, 90 degree is represented by j, rotation represented by j, then we have 180 degree and 270 degrees. Okay. There are some corrections here. We can take an example, say this A is not there, say your V is given by, say we have V is equal to 20 sin omega t plus 45 degree. Okay. Say this is my sinusoidal signal, and we can take this example to represent it by a phasor. Okay. So, here we can see the magnitude of this is 20. Okay. And yes. So, what we will be having basically is this is our real axis, here is our imaginary axis. Okay. And this is at an phase of say 45 degree. Okay. And this magnitude is 20. So, we can represent this phasor say as bold capital letter as what 20 cos phi plus j 20 sin phi. Okay. So, this is how we represent, and we can substitute the value, that is 20 cos 45 plus j into 20 sin 45. So, this is the phasor representation of this sinusoidal signal. Now, let us see the phasor equations. Okay. Phasor equations, suppose we have the expression x is equal to sine omega t. Okay, then if I take the first derivative of it, dx by dt is equal to omega cos omega t, or what I can write this as, this is omega, I can express this cos omega t in terms of the sine itself as omega sine omega t plus 90 degree. So what does this means? This means that the differentiation operation has what it has done is that it has multiplied the previous magnitude by a factor omega, and it has changed the phase angle by 90 degree. Okay, so the differentiation has resulted in a phasor with length increased by omega times, and it has been rotated by 90 degree with respect to the original phasor. So this is what does the differentiation operation. So in actually the complex notation, differentiation means, as I said, multiplication of the original phasor by j omega. So if in phasor operation, if I have a phasor written in terms of complex notation, then the differentiation essentially means that I multiply that phasor by a factor j omega. Now this multiplication by j will be rotating that phasor by 90 degree with respect to the previous one, and the multiplication by omega will be giving or will be multiplying the magnitude by omega. Okay, so this is what is done. So we can take the differential equation like this, say a1 dx by dt plus a0 x is equal to b0 y, the same expression, and this can be written as a phasor equation as what? See here, differentiation is involved. So what I do is say the phasor is x, then I multiply this x by j omega. So this j omega is being multiplied, and x I have, and this a1 value is my original coefficient here, plus we have the a0 x is equal to b0 y. Okay, and from here I can get the ratio of output, that is x divided by input, and this is b0 by j omega a1 plus a0. So this is what I get. Now this is my ratio x by y is equal to b0 by j omega a1 plus a0, and now I hope you remember that for the first order system, when we found out the transfer function, okay, that is we had the first order system, okay, that is a1 dx by dt plus a0 x is equal to b0 y. Okay, so when we found out the transfer function for this, what we did, we took the Laplace transform of both sides, and we took the initial conditions as 0. So what we had is a1 s xs plus a0 xs is equal to b0 y s. So from here we got xs upon ys, which we called as the transfer function, and that was b0 divided by s a1 plus a0. So this is what we have, b0 by s a1 plus a0. So remember, this is our transfer function which is defined, okay, and this is what we have worked out for the frequency response. Fine. So if by seeing these two expressions, we can see that if we want to convert from transfer function to the frequency response function, okay, in place of s what we have to do, we have to just replace this s by j omega. So if you replace this s by j omega, you will get the frequency response function, or what I have said is the frequency response function or frequency transfer function for steady state condition can be defined as g j omega. We are placing this s by j omega, and this is the output phasor divided by the input phasor. Okay. So this is the output phasor divided by the input phasor. Okay. Now let us see the frequency response for a first order system. Okay. So suppose I am interested in finding out the frequency response of a first order system. We can say take an example, a first order system has a transfer function, say Gs is equal to 1 by 1 plus tau s, and where the tau is time constant. Now what we are interested in? We are interested in finding out the frequency response function. Okay. So the frequency response function for this case will be what we are doing, we are replacing this s by j omega. So it is g j omega is equal to 1 by 1 plus s is being replaced by j omega and tau. So j tau omega. So this is there. Now we can find out the magnitude as well as the phase angle. Once we have the this phasor basically, okay, we can find out the magnitude and phase angle. And you remember this phasor is basically the ratio of output phasor divided by the input phasor. Okay. This is the ratio of output by input. So basically this tells that how many times the input has been multiplied, okay, in order to get the output. Okay. And how do we get this thing? It can be explained simply. These are just a small mathematical operation, and through those mathematical operation we can get that. So we have g j omega is equal to 1 by 1 plus j tau omega. Okay. So what we do is basically we basically try to represent this in the form of a complex number. Okay. So we after representing in the form of complex number, we try to find out the x component, we try to find out the y component, and once we have the x and y component, we can find out the magnitude as well as we can find out the phase angle. So this is what we are going to do. So to convert this in the form of a separate x and y component of the complex number, what is done is that the numerator and denominator are multiplied by this number with a opposite sign here. So this is what I am going to do, 1 minus j tau omega divided by 1 minus j tau omega, and so this what it makes is 1 minus j tau omega divided by, this will be 1 minus j square tau square omega square. Okay. A plus b into a minus b, that will be a square minus b square. So this is what I get, 1 minus j tau omega divided by 1. Remember j square is minus 1. So this is 1 plus tau square omega square, or what I get is 1 by 1 plus tau square omega square minus j into tau omega divided by 1 plus tau square omega square. So this is essentially my x component, which is the real part, and this is my y component, which is the complex part. Okay. So I can find out the magnitude for this one. Okay. Say if this is x, this is y, this is my real part, and here I have got the imaginary part. Okay. So this will be under root x square plus y square, and this phi we can find out tan phi as y by x. Okay. So, first let us find out the magnitude, that is the mod of g j omega, this will be under root x square. So, it is 1 by 1 plus tau square omega square whole square plus y square, that is tau omega divided by 1 plus tau square omega square whole square. Okay. So, this will be what we will be getting is 1 plus tau square omega square divided by 1 plus tau square omega square whole square basically. Okay. So, this will be nothing but under root 1 by 1 plus tau square omega square. So, this is what we are getting 1 by under root 1 plus tau square omega square. Okay. Yeah, and I can find out the value of phi, that is tan phi is equal to y by x. So, this I can get what is my y here. So, this is my y component basically, that is tau omega, okay, that is minus tau omega divided by 1 plus tau square omega square, and the x component is 1 by 1 plus tau square omega square. So, this is nothing but minus tau omega. So, this is my tan phi. Okay. So, this way I can find out the value of tan phi as minus tau omega. Okay. We can take an example basically to illustrate, say a system transfer function is given by say phi by s plus 1, and find what we have to do is actually find out the magnitude and phase of the output when subjected to a sinusoidal input of this one. So, we are given the sinusoidal input and we have the system as the transfer function. So, we have to find out the magnitude and phase of the output. Okay. So, to do this, what I can just give you a brief idea how we can do that, and basically this tells us how can we find out the system response in the frequency domain. Okay. And so, to do this, here you see that we are given Gs is equal to say phi by s plus 1. So, we can convert this by replacing s by j omega. So, this is phi by j omega plus 1. Okay. Now, we have to convert this into the complex number. So, basically what we are trying to do is that we will find out the magnitude of this Gj omega and the phase angle. Okay. And once we have the magnitude and phase angle, then we can find out the output phasor, okay, by multiplying the input phasor with the this G. Fine. So, that we can do. So, we can do the same operation here, that is I multiply with minus j omega plus 1 at the numerator and minus j omega plus 1 at the denominator. So, this is what I get 5 1 minus j omega divided by here this will be what, a square minus b square. So, we will have minus j square omega square plus 1. Okay. So, this is b square and this is a square. So, a square minus b square. So, this is 5 1 minus j omega divided by this will be minus 1. So, minus minus plus 1. So, omega square plus 1. So, this is basically 5 by omega square plus 1 is the real part, okay, minus j into 5 omega divided by omega square plus 1, this is our the complex part. Okay. So, from here I can find out the magnitude of it here that is g j omega, and this g j omega will be given by under root this one. Okay. So, 5 by omega square plus 1 whole square plus 5 omega by omega square plus 1 whole square, that is under root x square plus y square. Okay. So, this we can do, or what we can write this further is this one, this 5 square I think I can take out. So, this is there, and so here I will have 1 plus omega square, and here I have 1 plus omega square whole square. So, this will be basically 5 by under root 1 plus omega square. So, this is my value of g j omega, its magnitude, okay, amplitude. And I can find out the phase angle also by writing tan phi is equal to this will be what, minus omega, is it not? Yes, it will be minus omega. Okay. So, from here we can find out the value of phi. Okay. So, I get the value of phi, I get the value of magnitude. Then you see that we have this input. So, the input has got a magnitude of 4. So, whatever value I am getting from here, this omega of course we know, because we are given the input it is 2. Okay. So, I can substitute for 2 here. So, this will be 5 by under root 1 plus 4, or this is 5 by under root 5, or this is under root 5. Okay. Likewise, this will be minus of that is 2. So, minus 2. So, I can find out phi how many degrees it is going to be there. Okay. So, the output basically will be we have the input as 4 sine 2t plus the angle is say 30 degree. Okay. So, the output will be 4 times this magnitude root phi and then sine 2t, and here we have to actually find out the angle with respect to the reference axis. Okay. Remember this value will be this value is for our input. Okay. So, this angle we know, and the output will be this one. So, basically it will be this angle. So, we have to in the output expression we have to actually write this angle value, that is the value which is coming with respect to this one. Okay. So, that we can evaluate and put it over there. Similarly, we can take the example of a second order system. Okay. That is the frequency response for a second order system can be taken, and this is the transfer function for the second order system, omega n square by s square plus 2 zeta omega ns plus omega n square. Now, frequency domain response function we can get by if we replace s by j omega. So, if I replace s by j omega, this is what I am going to get. Okay. And I can represent this j omega in the complex form like this. Okay. Using the same procedure which we have seen earlier. Okay. And once we have this g j omega, I can find out the magnitude of it. Okay. I can find out the amplitude of it, I can find out the phase angle of it. Okay. And again, for a given type of input we can find out the output response. Okay. So, the sole exercise of this frequency response has been to find out the output for a given input. Okay. And the given the frequency domain response. Okay. So, I hope this is another way of doing your finding out of the output for the given input and for the given system equations. You can refer Bolton if you want to read more. Thank you.